All right, so the last portion of this section is the significance test. Again, I like to call it a linear regression t-test for the slope, but t-test for the slope is fine. So the null hypothesis is going to be that beta is equal to some hypothesized beta value. Now for us in this class, that is going to be a 0, 99% of the time, I guess. Here's how you calculate the test statistic. Remember, test statistic is always your stat minus your hypothesized value divided by the standard deviation of your stat. Remember, test statistics are z-scores. X minus your mean over your standard deviation. The mean is the hypothesized value. Standard deviation is the standard deviation of your sampling distribution. And your input is your statistic. Okay? To find the p-value, you use n minus 2 degrees of freedom. If it's a one-tailed test on the upper side, we find the area to the right. If it's less than, the area to the left. If it's two-sided, you find whatever tail is smaller and you double it. Okay? The hypothesized can be any value, but oftentimes, in fact, in this class, it's always going to be 0. Why 0? What's special about 0? Well, if it's 0, then your null hypothesis is basically saying that there's no linear association. And if it's not 0, then you're saying there is a linear relationship. Or if it's greater than 0, you're saying there is a positive relationship. And if it's less than 0, then you're saying there is a negative relationship. Okay? In fact, it is so common to have a hypothesized value of 0 and a two-sided alternative that computer output are designed around that. They actually give us a test statistic and a p-value. Well, first of all, you're never going to use these three values because this is the standard error of your y-intercept, your test statistic and p-value of a test on the y-intercept, which we will never do. This value here is a test statistic for the null hypothesis that beta is equal to 0. Now, if you want to have beta not equal to 0, you have to calculate that thing by hand. And, it'd be different. And then, if you run a two-sided test, this is your p-value. So this is beta not equal to 0. Now, if you have a one-sided alternate, so for two-sided, whatever. So if you want a one-sided alternate, we have to modify this. For a one-sided alternate, basically we're going to cut it in half because that's the two-tailed value. Divide by 2. You do have to be a little bit careful that, you got to make sure that it's a one-sided alternate in the direction of your sample slope. But normally that's going to be true. I'm not going to try to trick you or trip you up. But if you have a one-sided, you got to make sure you take half of this. Two-sided, you can just take it. So that's what we're going to want to do. We're going to want to use these things if we can, and usually you can. I got a little comic here if you want to read it. I used to think that's one of my favorite comics, but I'm not going to read it to you. All right, tipping at a buffet line. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we've got 12 data points here. Now, if we want to make this like an AP test question, I would not give you this table. You have the computer output. You got a couple graphs that you can look at. You really shouldn't need to use a computer output. Do customers who stay longer give larger tips? Charlotte, an AP Stat student who worked at an Asian buffet, decided to investigate this question for her project. While she was doing her job, she obtained a random sample of receipts, which included the length of time the party was seated and the amount that they tipped. Here's the data with some computer output. Do these data provide convincing evidence of a positive linear relationship between time and tip amount? So here's my computer output. Here is my original scatter plot. Here's my residual plot. And here is a plot of my residuals. This is a normal probability plot. It may have been a while since we've seen these. So instead of doing a dot plot or a box plot or a histogram for some crazy reason, I decided to give you one of these guys. So we need to know how to interpret that. All right, so I didn't leave you anywhere near enough space on this one, so we'll write small. Here we go. We're going to do a phantoms. P, parameter of interest. Beta equals the true population slope of the least square regression line using time to predict tip amount. For Charlotte at this restaurant during the time frame that these 12 times were randomly sampled. Maybe during our conclusion we'll be a little bit more wordy to be careful on the AP test, but that's good enough for now. H, hypotheses. Beta equals 0, which, I don't have a ho there. HO, beta equals 0, or alternatively, there is no linear association between time and tip amount. Against the alternative, that beta positive is greater than 0, meaning the ha is there is a positive linear association between yada yada yada. Assumptions and conditions, unfortunately we have to check a full liner here. Linear. Check it off. Residual plot doesn't have any pattern. Shows no pattern, so that checks. Independent. Let me just check it off. I probably should check it first, but whatever. 1, each party's tip amount is independent of any other party. And 2, the 10% condition. N equals 12 is less than 10% of all receipts. Oh, that's about receipts. Whatever. For Charlotte at this restaurant during the time of interest. Normal. So what we're looking for here is I want to look at the residuals to see if the residuals are symmetric with no outliers. But they're giving me a normal probability plot instead. In that case, we're wondering if the normal probability plot is linear, and it's approximately linear. So normal probability plot of residuals is approximately linear. So that condition checks. And then the last, no, not the last. Next one is equal standard deviation. So for the equal standard deviation check, what we're checking is, are these approximately equally distributed about the least squares regression line for all values of time? Now you might say, well, no, look at this. This is more spread out and this is pretty close. That's not equal spread. This is more spread out. This is pretty close. But the question, I mean, we only got 12 data points here. So the question is, are you seeing consistent, like fanning out? Like remember what it looked like whenever it failed. You know, it was close and then it's really spread out here. So close and then more spread out. We're not seeing that. So I'm going to say it passes. The residuals are equally spread about least squares regression line for all times. For all times of interest, all times seeded. And random, liner. She took a random sample. So again, I'm assuming you were at our lectures, this is going to be one of the trickier portions on our upcoming test. All right, now we're home free. Phantoms, N, name the test. Linear regression t-test for beta, or for slope, with degrees of freedom equal to 10, 12 minus 2. Test statistic, obtain a p-value. So this is where we're really going to save some time. Test statistic is just t equals 1.23. Our null is beta is equal to 0, so we can just take that value without doing any work. P-value. So we're good because beta is equal to 0. However, this is the p-value for a two-sided test. We're running a one-sided test. And we're running a one-sided test that's greater than, and this is greater than 0. So we're going to take half of that. Is 0.247 divided by 2, which is 0.1235. Make your statistical conclusion. 0.1235 is definitely bigger than 0.05, so fail to reject the whole. Conclusion. Phantom statement in context. We do not have convincing evidence that there is a positive linear association, that there, remember you always phrase it in terms of the ha, is a positive linear association between time seated and tip amount for Charlotte's customers for all of Charlotte's customers at this restaurant during the period of interest. Probably being a little more detailed than we need to there, but it's never a bad thing on the AP exam. So we do not have enough evidence. We do not have enough evidence in this data to conclude that there's a positive linear association. So our sample data is too weak to conclude a relationship in the population. All right, this last example is, there was a past AP question, a question number 6, you know how they are those investigative tasks that go above and beyond sometime, where they hypothesized that the slope was not 0, but the slope was equal to 1 or not equal to 1. In which case they had to do some, basically you just can't use either of these two values, got to calculate them by hand. However, I am not going to do it. We'll call that BAPS. Beyond AP statistic. All right, that concludes 11.1. Now we got to do 11.2.